And today we have Leonid Petrov, and he's going to talk about Schur rational functions, vertex models, and random domino tilings. Thank you for coming.
Thank you very much. Thank you very much for inviting me. So I'm in Berkeley now. So those who are at MSRI in person, please come to room 220 for questions. And I'm really grateful to this institution for their hospitality and the in-person semester. I'm going to talk about a joint work with Amol Agarwal, who's also here, Alexei Borodin, and Michael Wheeler. It's a very long preprint we just posted, so I'm going to, and I can talk about this for hours, but I'm going to highlight the main topics about rational functions and vertex models and random, well, domino tilings, not even random configurations. Anyway, so it's concerning the free fermion 6-vertex model, which is equivalent to the quantum affine superalgebra symmetry SL11. And if you add colors, like it was very common in the seminar, then you would have to go for SL1N quantum superalgebra. This is also a fermionic in one direction model, and there is an even longer preprint that was completed in January. The same people without me. And so let me first start with explaining the combinatorial nature of the boundary conditions that are here in our model, and then we put a probability measure on that model with many parameters. So before things get too complicated with notation, let me explain the basic things. So we are going to consider a 6-vertex model, which has 6 kinds of weights and 6 kinds of vertices. And I'm going to represent the represent these by upright paths. And I'm going to pick 2 of the normalizations of the weights. So these weights are color coded red and blue, and they're basically just differing by a constant. So there are 6 parameters, right? We start with A1, A2, B1, B2, C1, C2, and then we divide everything. So for the red one, we divide everything by A2, so that the weight of A2 is 1. And for the blue, we divide everything by B1, so that this weight is 1. And so, yeah. I want the model to be solvable, of course, so that it satisfies the Yang-Baxter equation, which interchanges the blue and the red. I mean, they differ by constant, so this color coding doesn't really matter. But after further specifying the parameterization of these AI, BI, CI, I can pick our matrix, the cross-vertex matrix, to be specified later, such that when I take the partition function in the Yang-Baxter fashion, namely fixing the numbers of paths at these endpoints and summing over all possible internal weights, internal configurations of paths, then the partition function of this object and the partition function of this object with the cross moved to the other direction with the same fixed boundary conditions, they're going to be the same. Furthermore, so this is the basic 6-vertex model business, and for probability purposes, I want my weights to be non-negative, right? So that every partition function that's finite is going to be, so every configuration is going to have a positive probability, non-negative probability weight, so that we can start talking about probability at all. Okay, so here's the vertex model in its full glory of the boundary conditions. So here's what I'm taking. I take 2 numbers, n and t. One of them, yeah, and so the lattice is half infinite, so it starts with 1 and goes infinite to the right. And one of them, n, is the number of paths here, and t is the height of the red part, which can be arbitrary. So t and n are independent integers, and then n and the height of the blue part should be n, because I want to impose boundary conditions as follows. So first of all, I start with n densely packed paths and the leftmost bottom corner, and then they must exit far to the right. So they must exit far to the right. And then everything else, every other boundary condition is empty. So I picked my weights normalized such that the weight of the B1 in blue is equal to 1, which happens infinitely often here. And the red weight of the empty vertex is also 1, which happens infinitely often here. So I have infinitely many configurations, which means I need to take care of normalizing things. But at least for every fixed configuration, the weight is well defined as a product of vertex weights. And yeah, so I take the weights for the red here and blue up there. And then I need some conditions which I forgot actually. So I forgot to include the conditions so that this thing is normalized, but it's something like well, it's some conditions on the parameters, basically some inequalities, something like xi minus yj over xi minus yj over sj square less than 1, and so on. So there are some conditions of the sort which help me normalize the things, which are open in the space of parameters anyway. Okay, in this way we get the probability measure with the weights, which I didn't tell you yet because it has too many parameters to talk about. So let me further digress and discuss a much simpler model, which is that of plane partitions, which is maybe a helpful analogy of a sort for somebody who saw this already. So I start with an empty room in 3 dimensions in the corner, and then add inside the corner several finitely many 1 by 1 by 1 cubes. And when I add the cubes, I create some configurations. Then I consider probability measure on all possible configurations where the probability weight of a configuration is proportional to q to the volume, where q is a parameter between 0 and 1. And if I should have started with erased paths. So this is a box configuration. Then I code the configuration by a path ensemble, which this path ensemble should resemble the ensemble of these paths in the vertex model, where they start somewhere, then they do something random, then they add at the prescribed locations. And here also the paths, they start here, do something random here, and then add at the prescribed location. So this is what I call like boundary conditions a la plane partition. So in the plane partition, in the Q-weighted plane partition, so here, for example, volume was 15, which you can count by counting like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, plus 3, 15. Right. So the normalization constant has a beautiful product form here. It's Suter McMahon, I think. Given that if you fix the number of boxes, you condition on the fixed number of boxes 30, then you get a uniformly random plane partition. So this model as a probability system was considered by Okounkov-Reshetikhin 20 years ago. And they also studied the asymptotic behavior when the picture becomes large. So when Q goes to 1 is an asymptotic regime, because there is a single parameter here. Is the asymptotic regime as Q goes to 1, which means that partitions with, so if Q is small, then Q to the volume gets very small when volume grows. But when Q is closer to 1, it means that you're favoring plane partitions with more boxes. So this is the asymptotic regime here. Using Schur symmetric functions, they extracted determinantal structure of this model and studied lattice asymptotics or bulk asymptotics, where by bulk I mean that you take some point of observation somewhere in the system where you see a random mixture of 3 colors, and then you zoom in, and what you see in after you zoom in is a kind of a lattice measure, lozenge tiling configuration, in this case, tiling configuration on the full plane, which has some remarkable properties. Namely, it's a so-called pure state, meaning it's translation variant and ergodic, in that it has constant proportions of lozenges of different kinds. And so they obtained this result. And what we can do in the case of free fermion 6 vertex model is an homogeneous generalization of these asymptotic results. But of course, today I'm going to talk more about the structure than the asymptotics. So here is the asymptotics I'm aiming at from the beginning. But then let's get into the details now. So I'm going to define the weights and yeah, before defining the weights, so let me show how to use the Baxter equation to compute the partition function. So in the plane partition case, this partition function has a beautiful product form. So in our case, in general, if you take the fully general 6 vertex model, then it's not going to be a product, but it's going to be a determinant instead. So but still you can use the Baxter equation to compute the partition function. Namely, from the initial model, you augment the lattice to the right, you add a bunch of crosses, n times t crosses, which have a fixed boundary condition. And then using the Baxter equation, you move the crosses to the left. So you start from this cross, you exchange it with these vertices and these, then these, and it leads to one red moving up, one blue moving down. And then you start and continue with 2 other crosses, and then all the other crosses you move to the left, and then you get the following structure. So because you need to preserve the boundary conditions. So here, before you move the crosses on the left, you had empty, so it has to stay empty here. And then here are the incoming paths, and then here are the outgoing paths. They need to be preserved. And because of this, the full red configuration here is going to be empty. And this configuration is going to be empty. And the only non-empty part is blue. And actually, it's going to be finite in the blue part, because my boundary conditions on the right dictate that paths need to exit far to the right. But once you past the n by n box, the paths have to be already exiting at these packed locations at the right of the n by n box. So what we get is well known. It's called the domain wall boundary conditions for the 6 vertex model. And in general, for the fully, for the not necessarily free fermion model, you would get a determinant for the partition function here, which is the so-called Isergin-Korepin determinant, and it's a Q deformation of the Cauchy determinant. And what we're after is actually for free fermion case. And yeah, by the way, this Q is not the same as the plane partition Q, so maybe I call it T. So in the free fermion case, you actually get T equals 0. So the free fermion case degenerates this Isergin-Korepin determinant into a product, because once you get rid of the second factor, that determinant now becomes a product, which is an exercise, I guess. So in the free fermion case, the determinant factorizes. Okay, so that's one of the sort of motivations why we would want to focus on the free fermion case. And of course, what we get out of the model is that we are able to compute multi-point observables in the free fermion case, which are unavailable in the general case. So so here's the now let's get, yeah, let me ask you, maybe, do you have any questions so far? Okay, so let me then define the weights. The red and the blue weights. As I promised, they differ by normalization, but then I also call blue parameters XR and the red parameters W theta. So that if you replace W theta by XR and renormalize, you get the same weights. And my weights depend on essentially 4 parameters. The 4 parameters and the differences of 4 parameters. The 4 parameters are W and theta, or W and theta, theta minus 2W, which vary in the vertical direction. I mean, depend on the horizontal on the vertical coordinate, and also they're indexed by parameters y and s minus 2y, and these guys they depend on the horizontal coordinate j. And then one can check that this normalization satisfies the free fermion condition, which has this form. So for the general 6 vertex weights, AI, BI, CI, you would get the free fermion condition to say this, and after a little algebra, you can check that these things satisfy this. And the blue weights are defined in a similar way. So there are essentially 4 parameters, but the weights depend on their differences. So if you add a constant to all the parameters, it doesn't matter. But because we are in the full lattice and the parameters actually depend on the horizontal and vertical coordinates, there is only 1 degree of freedom here over the whole lattice. But at each vertex, there is the free fermion condition, but there are 4 parameters at each vertex as well. Okay. And then the cross vertex weights, the R matrix, they also depend on W, theta, X, and R, so that they exchange W theta and XR parameters. So in this in the Yang-Baxter equation, red corresponds to W theta and blue corresponds to XR. So one can check that the Yang-Baxter equation holds, and it's a manifestation of the SL11 superalgebra symmetry as discussed in the existing works of Brubaker, Bump, Nakasuji, Friedberg, and company. So there are several papers discussing similar weights where you have the kind of the spectral parameter having 2 dimensions instead of 1. Okay, so then once you define these weights, because they're free fermion, the domain wall boundary condition factorizes. So here's my probability model where we take W hat in the top and then W at the bottom, and then the main wall partition function gives you this term, which is kind of a Cauchy-like determinant product, where at the top you have 2 Vandermonde-like expressions, except here is I less than or equal to j, and here is I less than j, but they're Vandermonde-like, except they're deformed in the Tokuyama style, and this double product is the standard which comes from the Yang-Baxter equation, because you started by adding these crosses, which have weight x minus w over x minus w over theta square. So you have to divide by that, which gives you this factor. So there are 2 terms at play here. Okay, so this Yang-Baxter equation plus the main wall partition function allows you to normalize the measure, and it has a nice product form. So now I'm going to talk about, of course, symmetric functions. So once you define this partition function, then what I'm going to do is I'm going to cut it here and then treat the top part and the bottom part for a fixed configuration in between as symmetric functions. So I'm going to call.
Leonid,
I'm going to take.
Leonid, before you go further, there is a question in the chat. What does the main wall mean?
No, I don't see that, but let me try. What is the main wall? Yeah, the main wall is the boundary condition in the 6 vertex model, which has this form. So there are paths that are choosing to do something like this. Okay.
And they come in packages with no space in between.
Yeah. So it's n by n.
Okay, right. I see.
Okay. All right. So yeah, here's the chat. Now I see the chat. Okay, I'll react accordingly. All right. So so I'm taking lambda to be a partition or a signature with n parts, however you want to call it. These are integers, and for each lambda, I take the shifted subset lambda I plus n plus I minus I, which just makes it all distinct and greater or equal than 1. And f lambda is going to be, by definition, is going to be a partition function of only the blue part where I fix the bottom part with the bottom locations where the paths enter. This is going to be lambda indexed by lambda. So this is f, and this is it, and the g is similar. So what we get is that partition function above was in secret the Cauchy identity for the f and g functions. So so here lambda is 7, 2, 1. So this is going to be 7 plus 3, 10, 2 plus 2, 4, and 1 plus 1, 2. So right. So the partition function is that when you squeeze them together and sum over lambda, you get the Cauchy identity, which we have proven above. Again, modulo some inequalities on parameters so that the sum converges. So f lambda and g lambda both are rational Schur functions or inhomogeneous deformations of Schur polynomials, which are themselves rational functions in all the parameters. And they specialize to ordinary Schur polynomials. Also, they specialize to factorial Schur polynomials and supersymmetric Schur polynomials under different specializations. So you get supersymmetric from G by just saying that Yj are all constant and Sj are all constant. So, for example, you get supersymmetric in this rather simple specialization. You get supersymmetric Schur polynomials in variables that are rational combinations of y, s, w, and theta. Anyway, so you get the Cauchy identity, which I already explained from the for the partition function. So this z is the same as above. So this allows me to define probability measure. Well, going back, I have to ensure that my weights are non-negative. That is doable. That can be done if there are some inequalities on the parameters. So I can define probability measure and study probability measure since I'm a probabilist. But we also explore the symmetric function properties. So let me first discuss symmetric function properties. So both f and g possess a bunch of explicit formulas, which generalize some of the Schur polynomial formulas. So f generalizes one of them, and g generalizes another, or two other. So f is a simpler object. It just possesses a Tokuyama type double alternant formula, which is here. So let me comment on that. So it's a double alternant type formula because you just take a determinant of a sort of like a power, but of powers, x to the power lambda j plus n minus j, but instead of powers, you take inhomogeneous powers. So these are combinations which basically just, well, there are k factors here divided by something innocently looking, but it helps to divide it by this. And what you get is this is because there are k factors. I call them inhomogeneous powers, and they actually play a role of power functions in some other properties. And they divide by the Vandermonde, also fine, and then you multiply by the deformed Vandermonde, which one can find in Tokuyama's formula. And this formula and this f boundary condition was already studied by Motegi quite recently, and he got formula which is essentially equivalent to this one. So this is the f function, and then we also get the g function. So the g function is not as so it doesn't have, well, it doesn't have a double alternate formula. What it has a Jacobi-Trudi type formula. So yeah, anyway, so the domain wall partition function you can get from this function by computing this determinant in the case of lambda equals 0. Right. So so there is a Jacobi-Trudi type formula for G, which follows from the orthogonality. So as I said, phi functions, they look like power functions, and in particular, they are going to be orthogonal on the circle, actually bi-orthogonal with respect to some other family of functions. So these phi are like positive powers, and then I take psi, which are going to be negative powers, analogs of negative powers, and then their products are going to be delta orthogonal on the unit circle. So this is the property where where psi k is essentially 1 over phi k, but with a different prefactor, and these guys are orthogonal, which means that I can use phi together with this orthogonality to extract G as a coefficient in the Cauchy identity. So there was a question. Let me look at the question. Do you have any further questions so far? Yeah, no, this is not this paper, but Dari, you can look at our paper and the reference there. Okay, so it's 2017 archive, I think. It's called Izergin-Korepin analysis of something free fermion 6-vertex model, I think. Anyway, so we can extract G as a coefficient by f, and this is a single variable orthogonality. So it's a dz in a single variable where the contour goes around y's but not around s minus 2y, and then by using the usual determinantal tricks, you can get G as a determinant of integrals of the extractions, basically. So it's a determinant of extractions, again multiplied by deformed Tokuyama style Vandermonde. So it's in y's. So in the variables, where variables, I think I treat w and theta as variables, y's are lattice things. So it's not a Vandermonde in the variables, but rather it's a constant sort of, which can be which is explicit, can be ignored. The main part is the Jacobi-Trudi type determinant, where these are lambda I plus n minus I, comma j, which means that it's, and so h functions are contour integrals, and this j dependence on j here is so in the usual Schur case it would be lambda I plus j minus I, or maybe lambda I plus n plus j minus I, but here j plays a slightly different role. So j plays a role of j is the index of this y in the integral, and still this is a well-known in the community, and it appears as a McDonald's 9th variation on the Schur team from 1992, I believe. So this sort of formula, this sort of function is known, and what we get is interpret this as a free fermion partition function with these boundary conditions. So for the G, again, you need boundary conditions like this. So you take lambda and then you start from a pact and get to lambda. So there's going to be a G boundary condition, and we get the Cauchy identity. So we have two objects, G and F, which are dual in the sense of Cauchy identity. So a lot of other work gives you a different explicit formula for G, which is very big. So I'm not going to comment on the details. We call it a Sergeev-Pragas type formula because for supersymmetric Schur functions, there is a formula which involves summation over pairs of permutations and pairs of subsets. So you take two subsets, then you sum over pairs of permutations, where D is the diagonal, is the length of the diagonal in the Young diagram lambda. So a similar summation exists for supersymmetric Schur polynomials, but we are unable to match this guy to the existing Sergeev-Pragas formula for Schur polynomials. Still, it has a similar flavor. So it's an explicit formula, explicit summation formula with two permutations, which kind of correspond to usual and dual variables, where this doesn't really make sense here, but in the supersymmetric Schur case, it does make sense. Anyway, so I'm not going to comment more on this. This is just another explicit formula which we don't use for anything probabilistic in this particular work. So okay, so let me now. So I formulated a bunch of properties of the symmetric functions, which are partition functions of the free fermion six-vertex model. These are very analogous to Schur polynomials. So because we are dealing with the six-vertex model, next two parts I'm going to explain ingredients from the six-vertex model, which are in particular beta ansatz operators A, B, C, D, which really help for, well, to get these formulas in the first place and to actually study probabilistic systems based on F and G. And if I have time, the last part is going to be about asymptotics. Maybe I don't have time, but it doesn't matter. So my next goal is to explain ingredients from the six-vertex model, which are helpful for the symmetric function picture. So these are the so-called beta ansatz operators, algebraic beta ansatz operators, A, B, C, and D. So because we're having an integrable lattice model, because it's a lattice model, we have operators which know how to act in tensor products. So we have a coproduct structure from them. So I'm going to define operators for a single vertex, operators in C2, 4 operators A, B, C, and D. Why do I need 4 operators? Because if I have a single vertex, then the vertical space is going to be C2. So I have a C2 with basis. So C2 with basis E0, E1. And this encodes the number of arrows in the vertical direction. And then in the horizontal direction, we have 4 cases, right? 0, 0, 0, 1, 1, 0, 1, 1. So I'm going to put them in a matrix and call the entries A, B, C, D, like every matrix should. So every 2 by 2 matrix should. And so so A E naught is going to be diagonal in E naught times the weight of this configuration. So A corresponds to 1, 1 in the horizontal direction. And then A E1 is going to be the weight of the fully packed configuration times E1. So B would involve, so B E1 is going to be weight of this times E naught, because it goes from E1 maps to E naught here. C is going to be, and then B E naught is equal to 0. B E naught is equal to 0. C E naught is going to be creating an arrow and going to be times E1, and D also involves D is also diagonal. It's going to be just involving the weights of these two, similar to A. So these operators, of course, if I take a single vertex, they depend on 4 parameters: XR corresponding to the horizontal coordinate, YS corresponding to the vertical coordinate. And because I'm in a lattice model, there are 2 structures. One coming from the lattice, when I take 2 vertices and stack them in the horizontal direction, then I get action in the tensor product. Because when I have 2 vertices, I can encode this by a basis vector in C square tensor C square, right? There's E naught E naught or E naught E1. So there are two vectors corresponding to the 2 spaces, and so I get and then I can take arbitrary tensor power of C2 and have all these operators A, B, C, D act in tensor powers. For example, in the case of 2 vectors, I can act by B on a tensor product of any two vectors. Actually, v1, v2 might come from arbitrary spaces anyway. But if v1, v2 come from C2 both, then B is these boundary conditions. So it's going to be always the sum of two terms. Well, depending on like where the arrow turns. So either it's BA, B tensor A, or it's D tensor B, and so on. So this lattice structure, even without any integrability, allows me to define my ABCD operators in tensor powers of the space. And integrability comes as a Yang-Baxter equation, and it allows me to, it gives me quadratic relations on the operators themselves. When I stack together the operators vertically, it means that I take a product of the operators in the same space. So for example, I get, if I first act by D, then by B, then I could have done dB in the other direction, but there are coefficients coming from the R matrix. So there are, these are R weights. So this follows from the Yang-Baxter equation. If you get B and D, which means that you're specifying boundary conditions here, then there is the Yang-Baxter equation, which implies a bunch of quadratic relations, a lot of quadratic relations on the operators A, B, C, D. And so we get this algebraic structure, which is basically the algebraic Bethe-ansatz that was pioneered by the Leningrad School in the 1980s. So yeah, these are these two structures, and then there are quantum groups associated to this, and so on. But we won't need those. Okay, so but what does it allow to do? So it allows to compute f and g as partition functions, because f is going to be so it allows to compute f and g. For example, for example, if I want to compute f, then so I take my lambda. So this is lambda, and this is like E, you know, this is E naught tensor, E naught tensor, E naught. And what this does is this is basically, so f is simply, you know, E naught times the action of product of b's on lambda, and here I'm taking a formal scalar product, for which you know these e's are orthonormal. So it's a coefficient by, so you take a vector corresponding to lambda, which is a, you know, E1 tensor E naught tensor E1 tensor E naught, depending on where you have arrows. Then you act by a product of b's, and then you take its coefficient with respect to the empty vector. So in this way, f and g, both the partition functions, they become just matrix elements of products of ABCD operators acting in the infinite tensor product. It's infinite, but you know, it's not that infinite. When lambda 1, you can just cut it here, so it's actually finite tensor product even. And the formulas follow from these two types of relations: quadratic relations and tensor product relations. So for example, there is an appendix with one formula by in the book by Korepin, Bogolubov, Zergin, and then one can basically extend by induction after very long computations involving induction and involving, you know, inductively applying products and tensor actions to build the lattice. So for example, you know, you encounter things like that, where you have product of D's or B's, and each D, you know, this is the action on, you know, in V1 tensor V2. So how does a product of D's act in a tensor product of two spaces? Well, you know, you use the tensor expansion, and then you do it for every operator. So you have a bunch of product like here, then you open it up, and then you get, in each tensor factor, you get a product of, so in the first tensor factor, you get a product of B's and D's in different order. And now you use quadratic relations to commute B to the left, so that B's are all to the left and D's are all to the right. In the second tensor factor, you apply commutating relations, quadratic relations to commute C to the right and D to the left. So non-trivial part is how to get this coefficient. So this coefficient you can get by inspection of what's going on when you commute, and which spectral parameters exchange in the commutation. So it can be done. This is one of the lemmas in the computation of G function. So so these arguments they lead us to both formulas, the double alternate formula for F and the long Sergeev-Pragas type formula for G. And the Jacobi-Trudi for G is, as I said, is from orthogonality is kind of a simple consequence of Cauchy identity, which is the Yang-Baxter equation, and the formula for F. So why is F determinantal? Well, you could do this, right? You could do this computation using Yang-Baxter and tensors for any vertex model. It doesn't have to be free fermion, right? But free fermion somehow magically leads to determinants. I'm not, like formulas tell you that you have to get a determinant, right? And in G case, you don't even get a determinant. So I don't know. So maybe my co-authors can comment on that. But the R matrix, which is involved in the commutation relation, it satisfies the free fermion condition, which leads to some simplifications along the way when you compute F. But you know, it's not that direct, because for G, for example, you don't even get a determinantal formula by using this method. So there's some kind of integrable miracle happening here, the free fermion miracle. Okay, any questions? Yeah, let me get to the second use of the ABCD operators, where we actually can use them to address the determinantal structure to get some probabilistic information. So I'm going to take, instead of taking the full tensor power, so instead of taking, you know, C star tensor infinity for all Z, so that's too big. So instead I take the Fock space. Fock space is a span of EJs where J is a semi-infinite subspace, semi-infinite subset of the Z. So I take only those configurations which are arrow configurations, which are densely packed to the left and empty to the right. And for each such configuration, I formally define, you know, E1 infinitely many times, then some combination of E1, E0 tensor product, and then E0 after that, E0 infinitely many times. So this is going to be my basis elements, which are going to be orthonormal. And the Fock space is by definition the Hilbert completion of that thing. So we don't even need Hilbert structure. We are going to be dealing with computations with matrix elements all the way. And for this Fock space, we're going to take normalized infinite volume limits of the ABCD operators. For example, like let's look at one operator A. So A is going to be the action of the A operator as you would take it. But here is a problem. The W weight is 0. The W weight is 1 only for the empty vertex. So if you just take the numerator, then there are two semi-infinite subsets, T down, T below, R above. And so if you just take the numerator is formally ill-defined because you have infinitely many non-zero, infinitely many non-ones here, non-one vertices here, and also infinitely many non-one vertex, vertices which are not equal to not having weight 1 in here. So you have to normalize it out. Normalizing it out, just basically you take a formal weight. So numerator and denominator are not well defined, but there is a simple infinite volume limit which makes sense of all of it. So in this way you get ABCD operators acting in the Fock space, We need this because we are going to use the fermionic structure in a second. And in this way, I still have my FG function still defined by action of B and D operators. So B and D, again, remember that these are just indices for certain types of boundary conditions on the left and on the right, which correspond to F and G. So my F and G are still matrix elements of these new operators. Here I also, well, at least I just need to add densely packed configuration to the left of 0. That's, that cancels out. It doesn't give you any action because it doesn't move any arrow from there. So back to probability. So the probability measure, which is defined by normalizing the F and the product of F and G with all the parameters, can be also written as a certain matrix element in the Fock space. So here's what I'm doing. I take the EZ less than N, which is the configuration with the densely packed, densely packed, of course, to the left of 0, and then there are N arrows to the right of 0, which are also densely packed. So I start from that, then I apply a bunch of D operators, which gives me a G. So this vector is a formally infinite summation of all the G lambdas times E lambda. Now I hit it by an indicator, which extracts me the single, the single lambda. So this I lambda is the indicator, which just it's a delta function which extracts me a single lambda that's going here, and then I hit it back with the B's, so that each B brings one arrow and moves it all the way to infinity, so that I have to be left with empty, and then I pair it up with the empty vector, which is densely packed to the left of 0. And then I have to normalize it. And normalizing is simple. You just put in the denominator, you just put the identity operator instead of the delta operator. And so the denominator is going to be the Z, which is that product, which is the partition function of the vertex model a la plane partitions, boundary condition. And this allows me to apply linear algebra to compute anything about my probability, because these are now operators that you put here in the yellow location. For example, we would like to get correlation functions. Correlation functions, instead of I lambda, you put the product of creation and annihilation operators. So correlation function is the probability that my set J of lambda, which is that Dirac C to the left of 0, fully packed, union with shifted lambda configuration. So the probability that this, where lambda is random, contains a fixed points, fixed up arrows at locations A1 up to AM. It's called the correlation function. This is equal to the same ratio of matrix elements, where you put the product of the creation and annihilation operators. So first you annihilate at AI, which means that it's either 0 if there was nothing at AI, or 1, or the annihilation, the modified vector, if there was something at AI, and then you add it back. But if there was nothing, then so this product eliminates all the wrong partitions lambda, for which this containment doesn't hold, so you hit it by annihilation first and then creation, which restores the lambda. And so if you just put it here, you get the correlation function. And the little c, they satisfy the canonical anti-commutation relation. And well, they are nice objects in general. Lots of determinant structures associated to them, Clifford algebra and things like that. We would be done if I knew how to compute the little psi's. Maybe I want to take annihilation to the right so that I annihilate something here, and maybe I want to take creation to the left so that I create something here, but then I need to hit it with a vacuum type vector. So that would be good. But now these D and B operators, they're pretty complicated. So it's really hard to compute individual P's with the ABCD operators. So instead of individual operators, we can actually put generating functions of CMC star in the following form. So this is my last slide, I guess, and maybe I have like one word about probability, but before that, let's take their generating functions. So instead of individual little psi operators, I'm going to pick special parameter combinations in the operators A, B, C, D, and pick their special combinations. Why do we do this? Well, because if I take special values as the second parameter, then this will kill in the quadratic relations. There are coefficients coming from the R matrix. Remember that, they have the form, R1 minus 2x1 minus x2. These are some combinations of the parameters. And this choice of parameters in the product in these operators, they actually kills some of these coefficients. So quadratic relations, which are quadratic bilinear relations, now become quasi-commutation relations. So basically, you can take psi and psi star, and they're going to anti-commute. So psi and psi star, they would satisfy the same canonical anti-commutation relations, basically. Sorry, this is not 0. I this wrong. It's 1. Sorry. Where you have I, the same is going to be 1. So if you look at these generating functions, then this one is sort of a delta function in the complex, generating function variables. And then these big psi and big psi star are expressed as linear combinations of little psi psi star, and we call this the inhomogeneous version of the boson fermion correspondence, because in the usual boson fermion correspondence, you basically have consider generating functions of psi and psi star with instead of this like big factor, you would have just some power like z to the j instead of all this, and then these generating functions are going to be exponents of the bosonic operators at the same time. So there is something bosonic about these psi operators. Right. So in this way, if I put if I put in my probability, if I put instead of this product, I put a product of several of these operators, like psi and psi star, psi, psi star, psi, psi star, psi, psi star. Then after expanding like this, where the coefficients are now certain inhomogeneous powers of u and v. So there are certain inhomogeneous powers of u and v here, which are like the notation that I used before. And in this case, I can take these operators, and these operators are already nicely commute with this D and B. Why do they nicely commute? Because psi and psi star are themselves D and B operators. They're coming from the same algebra, so they satisfy the same quadratic relations, and then you can commute them out. So by commuting them out, so here's what is done here in this formula. This is one of our main computations under the hood of the proofs. Is that instead of if you put these generating functions in yellow, then you can commute them out to the different locations and get an explicit product in the end times the determinant. So this determinant comes from the vacuum average of a product of psi functions, which is a weak type determinant in the Fock space. And after this, we can extract individual coefficients. So this thing contains some CJs, and this thing contains CJ stars and so on. And there there are many generating function variables which allow me to take a multiple integral using orthogonality that I displayed before. So there is inhomogeneous orthogonality, which allows me to extract the coefficient by the correlation function in here. And this is done by applying a 2m-fold contour integral, but because it's an integral of a determinant, it's at the same time determinant of integrals, right? So I get a 2m-fold integral of a determinant. This is the same as a determinant of double integrals. Because inside here you have a product part, and the only non-product part is the determinant, which allows you to take the determinant of double integral, and so we get the following result: that the probability that the correlation function, which is the probability that my random configuration contains fixed points, is given by a determinant of a 2-point function indexed by these points. And this 2-point function is called correlation kernel, and the point process satisfying this property is called the determinantal point process. And the correlation kernel is having an explicit form as a double contour integral of an explicit product function having all these parameters lumped together. So here are the integration contours. Yeah, so I guess I'll stop here. Basically, the only remark is that you can use this, but and standard approaches of steepest descent to obtain asymptotics of this kernel and get a generalization and the deformation of the Okun-Kovreshetikhin point process, incomplete beta process or extended discrete sine kernel, depending on all these different parameters. So you can get here's one of the results. So you can get a function which is equal to an arc integral from z bar to z, where z is some complex number, a parameter of the kernel, and it depends on all my parameters y and s and w and theta. So four infinite sequences of parameters. And functions like that, they're remarkable that all their determinants of all their diagonal determinants are between 0 and 1. They're real and between 0 and 1, even though the function looks crazy. But they are determinants of these functions. They represent certain probabilities. Okay, so let me finish by summarizing. So I surveyed the free fermion 6-vertex model, where at each vertex we take vertex weights that satisfy the free fermion condition, and this is the only condition. And we take as many parameters as possible which are left after these conditions. And of course, because we want Yang-Baxter equation, these parameters need to be depending only on vertical or only on the horizontal coordinate, and it doesn't. Yeah, we cannot take fully general parameters across the full lattice. No, they have to be like they have to be only through vertical and horizontal coordinates separately. So this defines generalizations of Schur polynomials, Schur measures and processes, which are the random ensembles I talked to you about. And then we get asymptotics, which are in the asymptotics. In the bulk, we get the deformation of the pure deep states. So we can introduce 4 sequences of parameters in this discrete sine kernel. And previously it was not known. Only there were known generalizations for inhomogeneity only in one direction, but not in both directions in the lattice. And on the technical side, we have the inhomogeneous Fock space, inhomogeneous boson fermion correspondence that is informed by ABCD algebraic beta ansatz operators. And the last thing which I didn't mention in detail, but there is some kind of inhomogeneous calculus where we have Taylor and Laurent type series for any functions f of u and v. And then there is a Cauchy integral formula, which is based on the orthogonality for extracting coefficients. There is a Taylor series in the sense that coefficients in the series can also be obtained as some kind of differentiation analogs for inhomogeneous space, which are difference operators at specific points. So that that seems like a fun observation here. All right, thank you very much.
Let's thank the speaker. Okay, let me start